Hello everybody, I'm Chakib Belgaid and today we will present you our work on the impact of Java virtual machines on energy consumption. Before we start, let's begin in some numbers. In 2013, more than 90 terawatts hour of electricity has been consumed only by data centers, and this number has increased up to 140 in 2020. Another example of this huge consumption is the supercomputer Fugaku, who alone consumes around 30 kilowatts each year. Therefore, reducing the energy consumption of ICT became a major concern. We always want to optimize this energy on both levels, software and hardware. However, with modern architectures, it's kinda complex. And thanks to the distributed system and services, this task didn't become easier. So instead of trying to do it all by ourselves, let's focus on single brick. And this time it would be the Java virtual machine layer. Before we begin in our study, we want first to describe the JVM. So basically, Java Virtual Machine or JVM is a middleman between the source code and the machine. Instead of trying to compile the code for every single operating system and machine, we will compile it only once and then let the JVM execute it in each operating system. Well, thanks to this approach, we can gather more insights of our code and its execution trace. Therefore, we can optimize the most repeated part of it in order to boost the performance of the program itself. And this is what we call just-in-time compilation or JIT. Now that we understood our scope, let's try to answer those two research questions. The first research question will be about the impact of the JVM choice on the energy consumption. In other words, does changing the default Java virtual machine affects the energy consumption of the software? And the second one will be about how can we tune this JVM in order to reduce the energy consumption even more for those softwares. To answer the first question, we gathered more than 85 JVM candidates from more than 11 providers, and then we ran a set of benchmarks on them to see their energy behavior. Moreover, each benchmark has a purpose to test a different aspect of code. We used the most famous state-of-the-art benchmarks, which are Da Capo and Renaissance. And in this slide, we can see the focus or the target of each set of benchmark. As an example, we used Aurora for event queues, and we used ASL for more data-oriented works. Now let's discuss our results and findings. As we expected, different JVMs exhibited different behavior. However, as our surprise, there were some tendencies. Besides OpenG9 and GraalVM, who had their own unique behavior, most of the Java virtual machines followed the behavior of OpenJDK, especially after Java 11. The interesting part of Java 11 is that most of the JVMs have opted for the dynamic code evolution, which is an optimization on virtual machine that was first introduced by Terava distribution in Java 8. Hence, for further studies, we have considered to use four representative JVMs, which are OpenG9, GraalVM, OpenJDK 11, and OpenJDK 15. If we zoom in OpenJDK as an example, we can see that each benchmark has its own optimal version, with special notice for reactors, who had suffered from some experimental features that were introduced in Java 11 and then got rolled back after the version 13. Now that we have covered the impact of the GVM choice on the energy consumption and found out that each distribution has its own spotlight, let's get deeper and study some configurations of those GVMs. In other words, can we tune the GVM in order to optimize even more this energy consumption? Despite the fact that OpenG9 was the most energy-hungry distribution in general case, as we have seen back in slide 15, OpenG9 exhibits a different behavior with the benchmark Aurora. Actually, it was by far the most optimal candidate. So we want to understand what are the reasons behind such behavior. So we have analyzed the execution trace of our candidates when they were running Aurora benchmark. And as we can see here, OpenGNI took only half time to finish the task. The main reason behind this is its number of parallel executions at the same time. While the number of active threads of OpenGDK and GraalVM was 2, G9 could raise this number up to 6, which is kinda surprising. The reason behind this is the different policy for memory allocation that was adopted by G9. G9 creates a non-collectible thread local heap within the main heap for each active thread, and the benefit for such cloning is a dedicated local heap for each independent thread, which means a faster access and no deadlocks. Further ado with the other experiments, let's start with the just-in-time compiler. Actually, we have been surprised that in 80% of the experiments, default JIT was the most optimal choice. However, for the garbage collector, the default one had only 60% success rate over all the cases. But when it succeeded, it saved up to 30% of the total energy consumption. In conclusion, to answer the second research question, we can say that most of the time the default configuration was the optimal one, especially for the just-in-time compiler. To help developers and practitioners choosing an energy-efficient GVM distribution and configuration, we propose a tool named gReferral. So, this tool takes a Java application as an input and launch a script to tune the GVM configurations in order to choose the most suitable one among 85 GVM candidates and versions that were made available by SD Common. Beyond the GVM distribution and version recommendation, gReferral automatically explores many garbage collector and JIT options for each distribution. As an example, we tried to reduce the energy consumption of Z4G. So we used gReferral, and here he used more than 123 configuration between distributions and garbage collector and JIT options. And as we can see, the most energy efficient one was OpenGDK with Java 15. However, the most efficient one was actually GraalVM when we used the JVM-C compiler. So, to summarize our work in a couple of words, we can say that GVM choice matters, and each GVM has its own spotlight and own weakness. Depends on the nature of the work. And the green one doesn't have to be always the most performant one, as we have seen in Zip4G example. Moreover, tuning your GVM can save some energy, but most of the case the default configuration is a good candidate, and it will save you some time to not study those tunings. Thank you, and if you have any questions or insights, feel free to contact us.